Hello there. So let's take a look at Chapter 8, Solutions Chemistry. So as usual, we'll take a look at some scenarios to whet our appetite for solutions chemistry. So a patient in the ER comes in with a head injury that's been causing some swelling in the brain. After considering your options, you request some mannitol to make a solution so that you can generate some osmotic pressure and reduce the swelling. We'll talk about osmotic pressure and talk about how the mannitol works. Later, you're asked to fetch a bag of concentrated saline solution from the stores. You find that there's a 2.75% solution and a second one with a molarity of 0.45. Which one is a greater concentration of solute? We'll take a look at that and calculating the concentration using a percentage and molarity and how that can be related back to the number of moles of solute in each bag. Finally, a patient with an intravenous drip looking for 2.5% glucose solution. However, the bag they give you has a stated concentration of 8%. So what could you do to create a 2.5% concentration of solution? We'll talk about that in the chapter as well. All very relevant for our healthcare professionals. Right, so, excuse me, I need a little drink. Thirsty work being a chemist. So, at the heart of any solution, you've got at least two components. You've got a small bit of one component, what we call the solute, and a large amount of the other component that we call the solvent. And we can take just about any combination of the three states of matter to produce a solution. It could be a small amount of solid and a large amount of liquid, like beer, or a small amount of gas and a large amount of liquid, like a carbonated drink, or small amounts of gases mixed with larger proportions of gases, like air, or it could be liquids mixed into solids. Just about any combination is possible. So that solution can form one of two basic types. It can be what we call a homogeneous solution. And that's a regular uniform solution where the solute to solvent ratio is the same throughout the entire solution. So sampling the solution at any position is reflective of the greater whole. However, we also have these heterogeneous solutions where either through lack of solubility or through gravity or something, if it's a mixture of solids or solids and liquids, we can have two or more chemicals which don't evenly mix in the solution. And this could be something like a whole basic range of things. Sand and water would be a good example. Depending on where we sample the solution, it could vary in concentration of solute compared to solvent. And so sampling the solution is not reflective of the greater whole. That can be a problem. However, it is pretty easy to recognize these irregular or heterogeneous solutions. If the solution is homogeneous, then the solution won't separate on standing. A heterogeneous solution would settle on standing. If the solution is homogeneous, then you can't use filtration to separate out some of the components. You can use filtration with a heterogeneous solution. And finally, a homogeneous solution should always be transparent. If it's cloudy or looks murky, if you can't see through it, then it's a heterogeneous solution. A homogeneous solution should normally pass all three of these standards. Should be transparent, shouldn't be filtered, and shouldn't be capable of separating by just letting it stand for a while. excuse me. So we'll always have a limit of how much solute can be mixed with the solvent to make a solution. This is what we refer to as the solubility. What's the maximum amount of solute that can be mixed with the solvent to make that solution? Now, how much solute you can dissolve, the solubility, depends on a couple of factors. First is the volume. If you increase the volume, you normally increase solubility. And if you decrease volume, you normally decrease the solubility. Second factor is the temperature. Solutes are normally more soluble as temperature rises, and less soluble as temperature falls. So to know the solubility limit for that chemical in the solvent, we need to know the temperature, we need to know the volume of the solution. So when you see a figure quoted for the amount of solute in grams in solution as a maximum, if it doesn't give any values, then assume that we're talking about 100 milliliters of solution at a temperature of 20 degrees Celsius. It could be a higher temperature or a different volume, but the data will state that, it will point that out. If it doesn't give you anything except the mass, then it has to be assumed that it's 100 milliliters at 20 degrees Celsius. Now, depending on how much solute is in solution compared to the solubility limit, we get a couple of different names for the solution. If the solution has an amount of solute below that limit, below its solubility limit, we say the solution is unsaturated because there's room for more to be added. Once we reach that solubility limit and we can't dissolve any more solute, we say the solution is saturated. A saturated solution has dissolved all the solute it's capable of dissolving. Now, it doesn't mean that you can't add solute to the solution. You can certainly add it, but it's not going to dissolve. It's not going to be part of the solution. But there are some ways to trick a solution into dissolving more of the solute. The most common way to make this happen is to raise the temperature. As we said, if you raise the temperature, you increase the solubility. But then carefully lower the temperature of the solution back down again. The slower the better. And as that temperature comes back down to the original temperature, probably room temperature, sometimes the solute stays dissolved in solution. We trick the solution into dissolving more by heating it up and carefully cooling it back down. Now, eventually nature catches on and it will spit out or precipitate the extra solute, but until it does, we refer to the solution as supersaturated. It's got more of the solute dissolved than it should be capable of dissolving. But remember, you have to trick it by raising the temperature and then carefully lowering the temperature. And even then, it's only going to work for a short period of time, maybe a couple of hours or maybe a couple of days, depending on the conditions. Now, if you want the extra to come out immediately, you could use a seed crystal of the same compound to act as a template for the rest to come back out on top of, or you could scratch the inside surface of the glass container. That jagged scratch surface again acts as a template, which causes the extra to crash back out of solution. So unsaturated when we've got less than the maximum, saturated once we reach our maximum, although we can still add more, and supersaturated when we trick the solution into dissolving more at that temperature by rising and then dropping the temperature. Raising the temperature to dissolve the extra, and then carefully dropping the temperature, making sure nothing precipitates out. So let's look at some examples. A solubility limit for water is 32 grams per 100 milliliters at 20 degrees. So if we had 24 grams in 100 milliliters at 20 degrees, That's less than the maximum possible, so the solution is unsaturated. If we dissolve exactly 32 grams in 100 milliliters at 20 degrees, we have reached our limit, and so the solution is now saturated. If we were to double the volume, 200 milliliters should be capable of easily dissolving 32 grams, so we'd say the solution is unsaturated again. Remember, increasing volume gives increasing solubility. If we took 100 milliliters again at 20 degrees, standard, and added in 36 grams, the solution would be saturated because we've reached our limit. That limit of 32 grams, and the extra 4 would just sit in the bottom of the flask. Just because you add it doesn't mean it's going to dissolve. So a saturated solution with 36 grams. However, if you heat that flask with 36 grams up to 50 degrees, that extra 4 grams will dissolve. Solutes are more soluble at higher temperature. So you get it to all dissolve at 50 degrees and then carefully cool the solution back down. And as long as there's no sign of precipitate, the solution would be considered to be supersaturated. So you can't just throw any chemicals together and expect them to form a solution. They've got to be able to interact with each other. They need to have something in common. Just like when you go to a party, you'll probably hang out with people that you have things in common with. Whether it's an interest in sports or movies or fashion, the more you have in common, the more time you spend in each other's company. And chemicals are exactly the same. The more they have in common, the more soluble they become in each other. And that common ground is about the kind of chemical bonding. We know about covalent compounds, where the atoms have differences in electronegativity of less than 0.5. We know about polar covalent compounds, with bonds which have a difference in electronegativity from 0.5 up to 1.9. And then we have, of course, ionic compounds or highly polar compounds, where the difference in electronegativity is close to the limit, or it goes over 1.9, and we're getting into ionic compounds. So we look at the chemical bonds, we look at the chemical makeup, and we find that as a general rule, like dissolves like. Non-polar chemicals like to mix and form solutions with other non-polar chemicals, and polar chemicals like to mix and form solutions with other polar chemicals. The reason being is that we've got a match in the kind of intermolecular bonding forces, how the molecules talk to each other. So non-polar compounds, as we said in chapter 7, would interact through induced dipole to induced dipole interactions. Polar compounds would interact through dipole to dipole interactions, and highly polarized compounds, which are capable of hydrogen bonding, would interact with other chemicals which are capable of hydrogen bonding. So if we look at a very general scale here for this, the polarity is increasing from left to the right as we snake through our picture, from hydrocarbons to benzene to dichloromethane to acetone to ethanol to water. We're talking about increasingly polar covalent compounds. So let me see, let's just draw a line for this. So there's a increasing polarity from left to right. So hydrocarbons with non-polar carbon to carbon and carbon to hydrogen bonds, you'd expect these molecules to react through induced dipole interactions. Similarly with benzene, it has non-polar bonds, but the bonds are more electron enriched, and this leads to more attractive forces. Then on to dichloromethane with polar covalent carbon to chlorine bonds, polar bonds which would allow for dipole to dipole interactions. Likewise with acetone, except stronger because there's a bigger difference in electronegativity. And then onto molecules like ethanol, and then finally water, which have a capacity for hydrogen bonding, and then a 100% capacity for hydrogen bonding in the case of water. So a couple of example questions from previous exams. Come on. If we imagine the chemicals from that previous graph combining together, hexane with water. Now hexane is purely non-polar because it just has carbon to carbon and carbon to hydrogen bonds. So it's trying to interact with other chemicals through induced dipole to induced dipole interactions. However, polar covalent molecules of water are trying to interact with others through hydrogen bonding. They don't speak the same language. They don't interact with each other. And they'll separate by density and with the water at the bottom because it's more dense. However, if you switch to hexane for methanol, methanol does have non-polar carbon to hydrogen bonds, but it's also got that oxygen to hydrogen polar group that we associate with water. So now they can speak the same language. They can hydrogen bond to each other and mix into a solution, so they form a miscible solution. We switch to butanol. We see how we've extended the part of the molecule which is non-polar. That's the part of the molecule that water doesn't like. But it does have a small portion which is compatible with. So we do see water mixing with some butanol to form a solution. But we'll have a much lower solubility limit, and then the two chemicals will quickly start to separate into layers. But you can get some to dissolve. However, if we switch to heptanol, we've now got a huge section of this molecule which is non-polar and non-compatible with the water. Remember, the water only likes this a little bit here. And we've reached a threshold, usually above 5 carbons in the main backbone of the molecule, where water is no longer soluble in the hydrocarbon, and so they separate into layers. The water on the bottom because it's more dense than heptanol. Let's try a few more. Still thinking about that table, and now 2 pages back. These are old exam questions. So which of the solvents from the previous page would make a good companion, a good solute for the propanoic acid here? We're looking for similarity in the chemical bonds because it would lead to a similarity in intermolecular bonding effects. So with that carbon to oxygen double bond, that's a polar covalent bond, of course. And that could lead to dipole interactions between molecules. We've also got that highly polar oxygen to hydrogen bond. And so we've got a capacity for hydrogen bonding between molecules. So acetone or ethanol, because of the carbonyl and alcohol groups that they have, would probably be the best fit. Second one, which compound is most polar? And to a degree, molecules are the sum of their parts. So if we look at this first molecule here, there's a part of the molecule which is non-polar, and then the end of the molecule is polar. We see that same polar covalent part on the second molecule, but the non-polar section of the molecule has increased. So collectively, the molecule is increasingly non-polar. So this would be considered more polar than the molecule on the right. The polarity, to an extent, is the sum of the component parts. Third one, similar idea. except now it's not the non-polar part of the molecule which is drastically changed, it's the polar part. We've got one polar covalent group in this molecule, but a second molecule has two polar covalent groups and would be considered a more polar molecule. Again, the sum of its parts. So this idea of like dissolving like also explains the chemistry we saw in chapter 3 for ionic compounds, which we said, my chair, which we said were capable of dissolving ionic compounds, water solutions. And that seemed a bit weird because they're dissolving and attracted to both positively charged metal ions and non-metals, which are negatively charged. How could they be attracted to both? Well, it's because a molecule of water is, of course, polarized. If there's highly polar covalent bonds, so we get one end of the molecule, as those dipoles stretch towards the oxygen, one end of the molecule which is electron enriched, that's going to attract positive ions like metals and sodium. And then the hydrogen feet, having the electrons drawn away, have a delta positive charge. And that delta positive charge on one side of the water molecule attracts the electron-enriched negative ions like chloride, the non-metal. So both sodium and chloride ions, as they break their bonds to each other, they both become attracted to molecules of water. And we say that the ions become solvated, surrounded by water when it's used as a solvent. So those ions have a greater attraction for water than they do for each other. As we saw in chapter 3, they dissociate in water into those individual ions. Now we're going to switch tracks a little bit to finish off our lesson for today, because so far we've been thinking about solids as solutes dissolved into water, but of course we can use gases as solutes too. And a gas acts a little bit different from a solid in solution. So while we expect solids to be soluble in water and increasingly soluble as temperature rises, as we can see from this graph here, a gas in water actually becomes less soluble as temperature increases. So we increase solubility of a gas by decreasing temperature. So you've got an open can of soda and you want to keep it fizzy for as long as possible, stick it in the refrigerator. Now, of course, anyone who's been fishing knows that this is true. Fishermen always go to the deepest part of the lake. That's where the sun finds it most difficult to warm up the water if it's deep water. And so that's the coldest water, and that's the water which has the highest oxygen concentration. And that's where the fish want to be, where the oxygen is, which they need for life. So gases are less soluble as temperature increases. Another factor we have to consider when looking at gases in solution is changes in pressure. Solids are not affected by changes in pressure, as we saw in chapter 6 with Le Chatelier's principle. As pressure changed, we only cared about the gases in the system. Only gases are affected. And this is described by Henry's law, which tells us that the concentration of the gas in solution divided by the pressure of gas around it is equal to a constant. So if you increase the pressure on a system, you'll increase the concentration of gas in that system. We see this effect when deep sea divers go down in the water. As they go down to greater depths, the pressure of the water around them makes gases more soluble. And of course, as we mentioned, Le Chatelier's principle explains why gases are more soluble as pressure increases. That greater pressure is like a greater concentration, and a greater concentration would feel like adding more chemical. So as we normally expect when adding a chemical, we move away from the chemical so that gas and solvent turn into more solution. The gas becomes more soluble as we pressurize the system. Okay, that is just about it for tonight. With section 2 missing class tomorrow because of the election, they're not going to finish chapter 8 this week. So there's no point in rushing and getting everybody else to finish chapter 8 this week. We'll finish chapter 8 at the beginning of next week. And that means that the exam for chapter 8 will not be next week. We will have a breather by a week before we come to the chapter 8 exam. Okay, we'll continue this on Wednesday in the 11 a.m. lecture online before meeting in class again on Friday for section 1. Okay, good night guys, stay safe, wash your hands, wear that mask.